Hello everyone, I am Khalid Salemi and I am PhD candidate at Laval University, and today I will be presenting our paper, a hierarchical DBSCAN method for extracting microservices from monolithic applications. So during this presentation we will discuss the context of the paper, including the problem we tackled and the research field. Then we will quickly go over the literature and talk about some of the baselines. Afterwards we'll present the proposed approach and its main components. Next, we will explain some of the research questions presented in the paper, and finally we'll conclude with a quick recap of the presentation. So, up until the last decade, most software architectural styles can be labeled as monolithic since they include all of the application's components within the same container, similarly to this example where all of the business logic, the data access layer, the user interface, and the database are grouped together within the same entity and are heavily coupled. These architectural styles often lead to maintainability and scalability issues. On the other hand, the microservice architecture emerged as a solution to these problems. It implements the software as a set of loosely coupled microservices that implement each a business logic and are independent from a technological perspective. Due to the large number of advantages provided by this design, this architecture has gained a lot of popularity in the recent years and has become the de facto standard when building new software. For some of the same reasons, and in order to keep up with the increasing demand and modern technological advancements, many companies have sought to update their monolithic legacy applications into the microservice architecture in this way. However, this process proved to be quite difficult and expensive. One of the crucial steps in this process was properly understanding the legacy application, which requires knowledge of the legacy codebase and its technologies, which are often very outdated and lacking correct documentation. So for these reasons, senior developers with specific expertise are needed to achieve this task and are often very expensive to hire. So automating this task would mitigate these issues and provide a faster and unbiased alternative. Our paper will focus in particular on the task of identifying how the monolithic application will be decomposed and on suggesting the optimal microservices. The refactoring and deployment steps, on the other hand, are out of the scope of this paper. So this is a sample of a monolithic application in GitHub called gpage store. In this case, the application is represented by its classes, and the new architecture is a set of microservices, each containing a subset of closely related classes. Prior work in this problem can be categorized by how they represent and extract information from the target monolithic application. Some solutions try to infer the relationships between the components by utilizing the execution traces and based on the assumption that components that interact together at runtime or for a specific use case often should be grouped together. Examples of these solutions are Mono2Micro, usage graph convolution network, and functionality-oriented service candidate identification. Other approaches try to utilize the availability of the source code and take advantage of the implicit information within it. One of the baselines that use this input is Bunch. Finally, there are solutions that use different approaches like the Git commit history or the application's documentation as the source code of the information. One example is a microservice extraction model which uses the Git commit history. Our solution will be based on the source code of the monolithic application. This choice was made due to the availability of this input, as we previously mentioned, but as well due to its ability to cover all of the components within the application. This isn't the case for runtime-based approaches because they are only able to include the classes that are already within the runtime traces. Like the previous example, we represent the monolithic application as the set of its classes, and as such the output would be like this, where our approach would be a decomposition that represents a list of microservices, each containing a set of unique classes. This approach can be split into two major components that work sequentially. So first, we have the extraction step. In this phase, we need a way to analyze the source code and encode it in a way that can be used by the subsequent algorithms. Its objective is to transform the source code represented by a set of text files into numeric datasets. Then, the second phase is the microservice extraction task. So, in this step, we utilize the previously mentioned datasets in order to group together the classes and infer the optimal microservices. We will now focus on the source code analysis task. Well, there are multiple ways we can approach this problem, And based on the literature, we have identified a couple of interesting ways to interpret the interactions between the classes based on their source code only. The first is the structural analysis, which focuses on the calls between the classes in the code. The intuition behind this view is that classes that often call each other in the code are dependent on each other and as such should be grouped together within the same microservice. The second view is the semantic analysis, which focuses on the terms used for naming the classes, its methods, its members, as well as the terminology used in the comments. Most companies follow certain coding guidelines when developing their applications, including naming conventions. As such, these names often include terms that are related to the business logic or the functionality of said component. For this reason, it is assumed that classes that are semantically similar should belong to the same use case and should be grouped together. So, how can we achieve the semantic analysis? We decided to use certain standard NLP pre-processing steps. So, for each class, we start by extracting the words in the class like its name, its methods, its members, and its comments. For example, here's a sample of the words extracted from the class card item. Here, this is its name. These are a couple of function names. Afterwards, we apply the camel case splitting. This means that we will use the camel case naming convention to split the names into individual words. So, for example, card item will be split into two individual words, card and item. The same for the rest. Then we filter out the stop words like by or in. And then we apply a stemming step. So this reduces certain verbs into their stem. For example, remove has become remove without an e at the end. And then you apply a df-idf vectorization step over the whole dataset. So the output of this analysis phase is an n by v matrix, where n is the number of classes and v is the number of words within the vocabulary. Structural analysis, on the other hand, can be achieved by any tool that can extract the metadata of the classes. Most tools transform the source code into a list of abstract syntax tree as an intermediate step, such as the following example. This is an abstract syntax tree of an if and else statement. And then these structures can be used to extract the calls between the classes. So this information can be used to generate a directed and weighted graph where the nodes represent the classes while the edges are the calls from one class to another. The weights of these edges represent the number of calls. The output of this phase is the adjacency matrix of this graph, where it is an n by n matrix, where n is the number of microservices, of classes. And after generating both datasets, how can we extract the microservices? We are trying to group together a set of classes where each class is represented by a numeric vector. This problem naturally fits into a clustering task where the microservices correspond to the clusters, the classes are the sample points, and the vectors are their features. However, there are a multitude of clustering algorithms with varying characteristics. In our approach, we propose DBSCAN, a density-based clustering algorithm. This algorithm groups together the samples based on the distance between them and on the number of neighbors within a certain threshold that they called epsilon. So samples that do not fit within these defined thresholds are on the other hand called outliers. Other decomposition baselines often define the number of microservices as an input of the solution. However, this parameter requires a good understanding of the monolithic application and a vision of the migrated version. As such, having this parameter as a requirement in a way defeats the purpose of automating the microservice decomposition task. This is one of the main reasons we decided to use DBSCAN, since it does not require this parameter. In addition, identifying outliers could prove a valuable information in the steps following the decomposition step, since these outliers could be thought of as the classes that are too general to be included in a single microservice, or classes that only have a technical purpose and don't have any relation to any business needs. Base action is an example of the former. But how can we use DBSCAN? DBSCAN and clustering methods in general rely on the distances or similarities between the samples in order to infer the clusters. For this reason, we cannot use the datasets we have extracted from the analysis phase directly. we need to define similarity functions that make use of the information within these datasets. And given that the structural analysis matrix and the semantic analysis matrix represent different aspects and different ranges of values, we can define the same similarity function for both of them. So for structural analysis, we use the function that we call similarity, which measures the ratio of shared calls between two classes. Its result is an n by n matrix where n is the number of microservices and the values are between 0 and 1. As for semantic analysis, we simply use the cosine similarity, whose results have similar shape, range, as well as size. Afterwards, we need to combine these matrices using a weight that we called alpha, which has values between 0 and 1, in order to preserve the normalized values. And so finally, we can use this similarity function with DBSCAN in order to generate the decomposition. However, is DBSCAN enough? Although it does solve the number of microservices requirement, the epsilon parameter is still needed to achieve satisfying results and to control this information indirectly. As such, we decided to use a variant that was called epsilon DBSCAN, which remedies this issue while preserving the advantages of DBSCAN. So this algorithm provides as an output a hierarchical clustering structure. It achieves this by running DBSCAN over multiple iterations and incrementing epsilon at each step, starting with 0 until a defined maximum value called max epsilon is reached. The result is a cluster hierarchy where the initial clusters represent very similar or identical points, while the final clusters represent groups of loosely similar points. Using this algorithm, the result would be a hierarchical view of the suggested microservices instead of a single decomposition. The final layer, like this example, could be thought of as a recommended decomposition. However, the whole structure could be used and visualized by the developers to select a more suitable layer or to customize the decomposition. The following layers in this case represent result sample. Each ellipse represents a microservice, while its border's thickness signifies the layer it was generated in. So for example, the initial layer grouped together the classes account and account DAO, then it added account form in a subsequent layer, and in the final layer it added user session despite having small interactions between them. On the other hand, in the initial layer, the microservices order and cart were created and then were joined together in the final layer because they interacted together at some point. And finally, we have base action as an outlier. So using this information, a developer might decide to keep the final layer because his objective is to lower the coupling as much as possible for his target microservices. Or, on the other hand, he just might decide to keep the previous layer since he prefers having highly cohesive microservices instead. For the next slides, we will discuss the research questions and the achieved results. So, how can we evaluate the performance of our solution? One possible alternative is to compare the decomposition generated by our approach to an actual microservice architecture. We applied this process on 3 open source microservices GitHub projects called Spring Pet Clinic, Microservice Event Sourcing, and Kanban, the boards. Let's take a sample of Pet Clinic as an example. We have 4 microservices and a total of 9 classes, each color-coded by their corresponding microservice. We merge these microservices into a single monolithic application, and then we apply our solution to generate decompositions such as this one. And now our objective is to compare these microservices in order to evaluate the performance of our solution. So we defined a couple of metrics called precision and success rate at k. Precision is defined as the mean percentage of correctly identified classes divided by the number of classes in each microservice. Success rate, on the other hand, is based on the precision metric, but calculates the percentage of successfully retrieved microservices instead. So for each project, we generate different decompositions by varying the hyperparameters of our approach. Then, we measured the evaluation metrics, and the following figure shows the box plot of these values for the precision metric. We can see that all projects had median values between 0.6 and 0.7. And the smaller project, Spring Pet Clinic, had varying results, while the larger projects were more consistent. As for the success rate, we started by using 0.5 as the threshold for the precision, and all projects had median results above 0.7, but very significantly by increasing the threshold, we can observe that lower medians, we had lower medians but more consistent results, and increasing it further, the results didn't change significantly, which suggests that our approach is able to confidently recreate the locations of over 40% of the classes. But how does our solution perform when compared with other baselines? In this comparison, we decided to select some of the previously mentioned baselines, which are Mono2 Micro, CoGCN, FOSCI, Bunch, and MEM. In addition, we selected 4 monolithic open source Java projects with varying scales for the comparison. First, we have Plants with 40 classes, GPET Store with 73 classes, ACME Air with 86 classes, and finally DayTrader with 118 classes. Additionally, we need to define new evaluation metrics since we can't use the previous one. So we selected 4 metrics: the structural modularity, which quantifies the cohesion within the microservices and the coupling between them. In this case, our higher values are better. We used as well the intercall percentage, which in the literature is used to measure the runtime calls between the microservices. So in this case, we use the static calls instead. Lower values are better. The interface number, as the name should suggest, is a metric for measuring the mean number of interfaces in the microservices. Lower values are better as well. And finally, we use the non-extreme distribution metric, which evaluates how extreme the microservice sizes are. So it penalizes extremely large or extremely small microservices. So the lower the values are, the better. And similarly to the other research questions, we varied the hyperparameter for each baseline and compared the results for each metric and project combination. These are the box plots for all of the results. We will focus on the first metric initially. So we can see here that our approach achieved the highest median value for 3 out of the 4 projects, with the exception being DayTrader. And specifically for GPET Store, our approach had the highest maximum as well. As for ICP and IFN, our approach achieved the best score in all of the projects, where we can see here. But more specifically for ACME, for the ICP score, our projects were significantly better than the other baselines, with only MEM having close results. However, for the metric NED, our approach failed to achieve the best values compared to other baselines. This was likely due to having very high or very low max epsilon values, which leads to having very small microservices with many outliers, or a small number of incohesive microservices when we have very high max epsilon values. But this hyperparameter isn't meant to be the defining choice for the final decomposition. It is more as the limit of the final layer, and the developer would be able to choose better in this case. So during this presentation, we started with the context of the paper, where we mentioned that we sought to automate the task of decomposing monolithic applications into a microservice-based architecture by recommending a set of potential microservices. Then we provided a quick literature review with other solutions categorized by their input, which could be execution traces, source code, or the Git commit history. Afterwards, we described our approach, where we presented the step needed to execute the semantic and structural analysis, their output, and the clustering algorithm used to generate the decomposition. Then we evaluated our approach by comparing the decomposition with manually designed microservices, where our solution managed to mostly recreate the original microservices with a median precision around 0.65. And finally, we compared our approach to other baselines using different metrics. Our approach managed to improve over the state of the art in 3 metrics that encode the cohesion of the interactions between the classes, but at the cost of more extreme microservices. So any questions?